Okay, continuing on with the fundamental theorem of calculus. Today we're going to work on the fundamental theorem of calculus with what's called the chain rule. So we'll just start out with an example. I want us to find dy dx for y equals to the integral from 3 to x squared of f of t dt. Okay, now going back to part 2 of the fundamental theorem of calculus, this right here, the integral of f of t dt, should be or could be represented by big F of t. That would be whatever the antiderivative of little f is. So that would actually be big F of t from 3 to x squared, and that would be whatever big F is evaluated at x squared minus whatever big F is evaluated at 3. Okay, and then we would want to take the derivative of it, because these are actually still y equals to. So if I were to write out the derivative of big F of x squared minus big F of 3, well, what is the derivative of big F? The derivative of big F, again by the fundamental theorem, is little f of x squared. But notice it's x squared, so we have to apply the chain rule, the derivative of x squared, and then we have to take the derivative of f of 3. And what's f of 3? I know I don't even know what f is, little f or big F, but what should it equal to? If it's f of 3, that means we're going to substitute and plug in 3. We're going to have a constant. So the derivative of f of 3, no matter what it is, because it's a constant, this is going to be 0. So then all we have left is the derivative of x squared, so 2x times f of x squared. So this is the fundamental theorem with chain rule and where it comes from. Now, you don't need to do this whole process every time you do the problem. I just want you to notice that if you have some limit, whether it's upper or lower limit, that is something other than an x, you're going to have the chain rule. Okay, and this kind of goes back to remembering and realizing that the fundamental theorem of calculus stated that it had to be the integral from a to x of f of t dt. Okay, a to x, some constant on the bottom and some variable x up at the top. So let's take a look and do a few more examples. So let's find dy dx. So let's see, let's let y equal to the integral of 3 to 2x squared of the square root of cosine t dt. Okay, and again, just like yesterday, the derivative of the integral is just the function itself. But again, what's different today is that we have a function other than just a simple little x up in our upper limit. So we're going to plug in the 2x squared in for our variable t, so that means square root of cosine of 2x squared. And then don't forget to derive the 2x squared from our chain rule. So we get 4x square root of cosine 2x squared. It really is just as simple as that. But the important thing about this is not forgetting that you have to do this. So let's practice with this. So again, upper limit requires the chain rule. So the derivative of an x cubed is a 3x squared. Then we have the cube root. Now this is t squared, so when we plug in x cubed, it's going to get squared and then plus 1. So that's going to be an x cubed plus 1 on the inside. How about we throw one with some trig in here? 2 to tan x. Now one thing I need you guys to notice is that the constant lower limit, we don't really care what it is as long as it's some number. It can be 2, it can be 4, it can be 5, it can be 100, it can be a million, no matter what, as long as it's a constant, it's going to be the same. And the reason for that is going all the way back to here. When you take the derivative of the constant, it is always 0. So let's continue on with this problem. I need to take the derivative of the upper limit tangent. which is secant squared x, and then 1 over 1 plus tangent squared x. And we need to simplify this. Any of you guys know how we can simplify secant squared x over 1 plus tan squared x? Secant squared x and 1 plus tan squared x, that's one of your Pythagorean identities. They are equal. This equals 1. Let's just go ahead and find d dx of the integral of from 2x plus 1 to 3 of the square root of sine t dt. Now, just like the one we talked about yesterday, since we have our lower limit on the bottom, we need to flip it up to the top and make it negative. So this is negative d dx of 3 to 2x plus 1, and then our f of t, which is square root of sine t. So once we do the chain rule, negative 2 square root of sine 2x plus 1. Okay, one last one. What do you think about this one? The integral from x to 2x of 4t plus 1 dt. Notice we have an upper limit and a lower limit with a variable in it. You need to remember that the fundamental theorem says that it has to be a constant. So we are going to have to split this up into 2. We are going to have to think of this as the integral from x to some value a of 4t plus 1 dt, and then add it to the integral from a to 2x of 4t plus 1 dt. Now, I would suggest just putting an a in there as opposed to a number, because no matter what, that number won't matter. And I don't want you guys to integrate and then take the derivative. Okay, remember we're trying to use the fundamental theorem here, so let's go ahead and apply that. Okay, I'm going to switch this one because the x was on the bottom, and then the other one stays the same. Now we're going to actually apply the FTC. So we have negative 4x plus 1 plus the derivative of 2x is 2 times 4. And be careful right here, we're plugging in a 2x and then plus 1. So we have negative 4x minus 4 plus 16x plus 2. So we have 12x plus 1.